So students, in our last class, we have been talking about the dynamics of system of mass particles, where we talked about the group dynamics, group kinematics and group kinetics. Today in our class, we will be talking about the application of the theory that we have discussed so far. So we begin with this example, which is example 1. Problem number 4/7 taken from the book of Merriam and Craig. And what we see from here, that we are given the three small spheres which are connected by the cords and the springs and are supported by a smooth horizontal surface, right, like this. Now, if we are saying that a force F that is equal to 6.4 Newton is being applied to one of the cords like this, find the acceleration A bar of the mass center of the spheres for the instant that is being depicted here. So this is the, we know that these are the system, and important thing is that to note that this entire system is placed on a smooth horizontal surface. We can assume that to be the top surface of any smooth table. And we have to find out the acceleration of the center of mass of this group. Let us suppose hypothetically that this crosshair sign C indicates the center of mass of this entire group. And we note here that this problem is basically, we see that this problem is basically the problem of Newton's generalized application of Newton's generalized second law, which states that F bar E that is equal to mc times A bar bar. So in this case, if we consider, we note that this system is constrained to move only along this horizontal surface or in the xy plane. So the acceleration of the center of mass of this system will be, therefore, it's going to be only along the x direction, and it will not be having any other component along the other directions. So if we note that this is a vector equation, so if we express this F bar E, remembering that this represents the sum of all the external forces which are acting on the system, we can say that it will be F I cap. The force is acting mainly along the x direction, so it will be F I cap, plus we will be having the normal reactions which will be from applied by the table surface on the respective masses. We can call these normal reactions as N1, N2, N3, which will be the normal reactions offered by the surface of the table on the mass M1, that is N1, on the mass M2 will be N2, on the mass M3 will be equal to N3. And then obviously we will be having the gravity forces. So it will be minus M1G, minus M2G, minus M3G. All will be acting along the Z axis. So Z axis being perpendicular to the plane containing this XY horizontal surface. So we note further from here that the acceleration of the center of mass of this system, since this entire system is constrained to move only along the x-axis or only along this horizontal direction, so it is to be noted that the acceleration of the center of mass will be only along the x direction. So we can therefore say that it should be equal to mc means the sum of the three masses m1 plus m2 plus m3 into A bar x, the x component of the acceleration of the center of mass, which happens to be the total acceleration of the center of mass in absence of no other component of accelerations along the other directions. So it is pretty clear from here that acceleration of the center of mass A bar x, which happens to be its total acceleration, is equal to F divided by M1 plus M2 plus M3. That means we take only the I component of the forces from both sides of this vector equation and can thus write to be equal to 6.4 divided by 0.8 plus 0.3 plus 0.5 which happens to be 1.6 kg. That will be the total mass of the system, and 6.4 divided by 1.6 obviously will give us the acceleration of the center of mass as 4 meter per second square, and that will be in the positive direction. So we can say from here that the acceleration vector a bar bar of this system is going to be equal to 4 I cap meter per second square. So that is going to be our acceleration of this entire group. So this particular problem, it indicates that how we can apply Newton's generalized second law in order to find out the acceleration of the center of mass. So we see from here that this simple equation, generalized Newton's second law, helps us to find out the acceleration of the center of mass of this entire system. So I think that this problem is pretty clear, and this is the fundamental problem, and we can of course cross check the answer provided for this problem. So if we go back to the answer section of this book, we can find out this answer of this problem, which will be 4 by 7. So we think that this will be somewhere here. So quickly we can go through this this thing to find out the acceleration of the center of mass, and it is being mentioned as 4 a bar equal to 4 meter per second square. So that problem is pretty obvious, and we can very easily solve this, but we need to show all steps clearly and put our logic that why it will be something like that. Now once we have solved this application, let us now go to our next problem, which is our second problem of today's class. So this is example 2, we can say. This is again, this problem is from the book of Merriam and Craig, and the problem number is 4 by 17. So here now we are having, earlier we are also having 3 mass systems connected by the springs and the cords. Now we are having the 3 light spheres welded to the rigid frame. So we see that if we recall our theoretical discussion on the groups dynamics, you know that we discussed about the rigid system. The rigid system we discussed in our last class. We discussed it in connection with n equal to 2, that is the total number of particles comprising our system, we take it to be equal to 2. But the thing that we had mentioned regarding this, I said that it is applicable for any number of masses. So let us go and see this. We are considering n is equal to 3. So our total number of masses in this group is actually equal to 3. So it is said from here that the 3 small spheres, these are the 3 small spheres, we can consider this to be equal to m1, the mass 3 kg. This is m2, that is the mass 4 kg, and this is m3, that is the mass 3 kg. So m1, m2, m3 are the 3 masses which are shown here and are welded to the light rigid frame in this manner, which is rotating again in a horizontal plane about a vertical axis through the point O. So again we note that this is again in the horizontal plane. So all these self weights are going down the plane, or it is along the negative direction of the z axis. If we suppose that this is our x axis, if we suppose this is our y axis, then the z axis will be the perpendicular to the plane of this figure, and of course the self weights of these systems are going down the plane. That means they are acting along the negative z direction, and this entire system is connected with this rigid frame and massless frame, of course, and which is rotating about a vertical axis. That means this rotation is taking place along the z direction, and the angular velocity of this system is being given to be theta dot equal to 20 radian per second, and it is shown in the clockwise direction if we look this figure at this figure from the front. That means, so to say, we can say from here that in our case the omega bar or the angular velocity of the system omega cis is being given to be equal to minus 20 k cap so much radian per second. If we try to express it in vectorial notation, so that will be our system's angular velocity. Now it is said that if a couple MO, this is the couple MO, which is also in the clockwise direction when looking from the front, 30 Newton meter is applied to this assembly. For 5 seconds, we need to calculate the new angular velocity theta dot prime. The initial angular velocity is being given to be, this is the initial angular velocity, and this constant torque of 30 Newton meter is being applied onto this system continuously for 5 seconds, and we need to calculate the new angular velocity of the system. And we see that this, in order to do this, we see, note that the couple is being given constant and it is being applied for certain seconds. So, and we need to find out the angular velocity. So ideally, this problem comes and falls under the category of the principle of equivalence of, so we can write it that it comes under the principle of equivalence of angular impulse, angular momentum. So we see that this is actually the angular impulse, angular momentum equivalence principle. So this we are going to apply in this problem to find out our things, because going by the statement of the problem, we immediately recognize that here we can apply this principle of angular impulse, angular momentum. Note that the whole thing, it is to be applied about the z axis. So the self weights of these systems are not contributing anything into our equation, and all the bearing reactions here, if we disclose the free body diagram, if we take the free body diagram of the system, obviously here the bearing reactions will come. But since all these bearing reactions will be actually intersecting the z-axis, they also will not contribute anything into our angular impulse momentum equation if we go to take all of them about the z-axis. So we therefore, the fundamental principle that we will be going to write, of course, is this, that is m bar a is equal to h bar a dot. We see that we will be going to use this equation. We note from our theory that this equation is applicable under 3 possibilities. First possibility is that we can apply it with respect to an inertially fixed point. So here, instead of taking the moment center as an arbitrary point A, we know that this equation can be written with respect to a inertially fixed point, and the inertially fixed point in this system is evidently the point O. So what we are going to do, we are going to write this equation, about point O like this. And another thing to be noted is that with respect to a fixed point, it does not matter actually whether I am going to write the relative or absolute angular momentum. So I do not use any subscript specifying whether the momentums are absolute or the relative, although in this case, they both will be same. So we note that because of the presence of this angular velocity, we just note from here, if we see the masses will have thus, because all are connected by these rigid links. So we see that the corresponding velocity because of this rotation will be, this will be the velocity which we can say v1, and this velocity v1 vector will be something like this. Then the velocity of the second mass m2 will be like this, that is going to be our v2, and then we will be having our this thing, that is, we can write it here this way. We can say this is m3, and we can show the velocity vector of the third mass, which will be going to be perpendicular to this arm and consistent with the sense of rotation. This will be your velocity vectors. And we can see obviously from here that the magnitudes of these velocities, that means v1, that is going to be equal to 0.5 times theta dot, where theta dot is angular velocity at any point of time. We see that it is v2, that is going to be equal to 0.4 theta dot, and v3, that is going to be equal to, we note from here that it is going to be equal to 0.6 theta dot. So we are having these, the velocities that we are getting. And from this equation, we can write, applying the principle of impulse momentum about the z-axis, we can say that we can write this equation in this manner. We can say that it is integration from definite time, say time interval t1 to t2. This we can write it as m bar o dt, that is this impulse, will be basically equal to h bar o at time t2 minus, we can say this is h bar o at time t1. Now again, this is a vector equation. We can bring down the corresponding scalar equation. In this case, we are going to take the whole thing about the z-axis. So we can therefore say from this equation that it is integration, so it is integration from t1 to t2. We can write that this is mo dt, taking the z-axis, z component of the whole thing. We can say this is ho at t2 minus ho at t1. So we just take here, the equation is taken and the z component of the equation is written. So all these will be about the z-axis, z component here it is written here. So this is the z component of the forces. And we see from here that these are your velocities. So quite naturally, we can write from the above sets of velocities, we can say that the angular momentum, we can say that HO at any point of this entire system is going to be equal to the moment of momentum, so for all these particles. So obviously, this is going to be equal to m1. This is the thing. We can write here the corresponding masses also. We can say the mass m1 is mentioned here as 3 kg. So this is 3 kg. Mass m2 is mentioned to be 4 kg. And finally the mass m3, which is mentioned to be equal to 3 kg again. So we can say from here that HO will be equal to this 3 into 0.5 theta dot into 0.5. So ultimately this becomes 0.5 square, plus we can say this is 4 into 0.4, 4 into 0.4 theta dot, again multiplied by 0.4. So again it will be 4 into 0.4 square theta dot, plus we can say this is 0.6 square into theta dot. So if we see from here that this angular momentum at any point of time is given by this equation, 3 into 0.5 square plus we can say 4 into 0.4 square, plus we see that it is 3 into, sorry, here we missed the mass, it will be 3. So 3 into 0.6 square. So we can write this in a proper manner, that it will be 3 into, so we can write this will be 3 into, and we have this plus sign. So 3 into 0.6 square, this whole thing multiplied by, you see, this is going to be equal to theta dot only. So we can say this is our angular momentum of this group about the z-axis at any point of time. So we can say that this is going to be HO, the angular momentum about the z-axis. So that is equal to, we can say this is going to be 3 into 0.5 square plus, we can write 4 into 0.4 square plus, we can say 3 into 0.6 square, and the result turns out to be as 2.47. So we can say this is 2.47 into theta dot. So this is going to be my angular momentum. We should give the unit here. We know that the unit of angular momentum is kg meter square into second to the power minus 1. That is going to be my unit for this angular momentum. So here we can safely write this equation and can say from here, considering time t1 to be equal to 0 and t2 equal to the duration of the time, that is going to be 5 seconds. So we note from here that this integration, if it is performed from t1 equal to 0, so we can write it is from 0 to this is going to be applied for 5 seconds. So our t2 we can take it to be as 5. So we can say it is integration from 0 to 5. This is the moment magnitude is constant and it is equal to 30 Newton meter. So we put this numerical value. So this is going to be 30 dt. So that is going to be equal to 2.47 into, we can say this is theta dot at t equal to 5 minus, we can say this is going to be theta dot at t equal to 0. And we need to remember here one thing very important, that we need to actually be careful about the sign of the whole thing. We note that here both the angular velocity and the angular momentum, they share the same sign. So therefore same sign it is there, so we do not bother about it. But if it is such that this angular velocity, instead of acting in this direction, had it been acting in this direction and your moment is in this direction, then we need to consider this theta dot at t equal to 0 as minus, because the angular moment, because of the fact that the moment is clockwise and the angular velocity is anti-clockwise. So when there is this mismatch of the senses, we need to be very careful and the respective sign allocation needs to be done. In our case it is simple, so we do not have to bother for it, and we can therefore say it is 30 into 5 is equal to 2.47, and it is being mentioned theta dot at t equal to 5, we say theta dot prime at it is actually with which the angular velocity is designated. This is the notation, and the initial angular velocity is being given to be 20 radian per second. So this is going to be our equation for us. So we can say from here that theta dot prime is going to be equal to 30 into 5 means it becomes 150 divided by 2.47 plus 20, so much radian per second is going to be our angular velocity. So we can write this is 150 divided by 2.47, and then we need to add to it this 20, and it turns out to be 80.728. So we can say 80.73. So we can take this as 80.73 1.73 radian per second, and it continues to be in the clockwise direction. So that is going to be our answer for this particular problem. So here in this case, we note that this problem here we can solve it evidently by this method of principle of angular impulse and equivalence of angular impulse and momentum principle. So going to this answer, just to check, we see that this theta dot prime is going to be 80.7 radian per second, which in our case is, we have calculated it to be 80.73 radian per second. So here again we note from this problem that we can apply this principle of equivalence of angular momentum and the angular impulse. So students, we have solved so far two problems. The first example highlighted the application of generalized Newton's second law of motion, and the second example that we have considered here highlights the principle of equivalence of angular impulse and angular momentum. I hope that you have understood this problem. Again, I am telling, there is one important thing that to note in this case is the sign of the angular velocity and the angular impulse vector. In this present problem, it happens to be both identically have the same sense of their direction, but if the angular velocity, instead of showing in this direction, had it been in the opposite direction, then we need to consider, because in this case the moment will be in the clockwise direction and the angular velocity will be in the anti-clockwise direction. So we can take any one of it as plus, then of course the other one will be considered as minus. That means if we decide to take the sense of the angular velocity which is in the counterclockwise direction as to be positive one, then the corresponding the sense of the moment, which is if it is acting in the clockwise direction, has to be taken in the negative sense. So in that case, the plus and minus will come into our equation and will therefore be, we need to be very careful. However, for this problem, our thing becomes simple because both of them are sharing the same sense. So with this, we next go to the next problem. This is our example 3. So this is our next example that we are going to consider. This is our example 3 we can take. This is example 3 and the problem number is taken as 4/24 from the book of Merriam and Craig. What we see here, we are being given a system and here we see that n is equal to 2. That means we are having only 2 masses in our consideration. And again, as seen from the figure, that it is actually a rigid system, n equal to 2, and the thing is that it is actually the rigid system. In our earlier problem also, if you note the problem just now that we have discussed here, this is also an example of rigid system. So this is also an example of the rigid system. So but our example 1, you see, where the masses are connected by the cords and the springs, this is not the case where we have the rigid system. And here also our number of masses is n equal to 3. So this is the number of masses that we are getting. Now, if we see from here that this is our problem, we note that we are being given 2 spheres which are rigidly connected to the rod of negligible mass. So this is the 2 spheres, each having the mass 1.5 kg, 1.5 kg each, and are connected by a negligible light rod. So this is again the rigid system consisting of 2 masses. All masses are equal. And we see that these 2 spheres are rigidly connected to the rod of negligible mass and are initially at rest on the smooth horizontal surface. So this is a smooth horizontal surface on which we have placed this system. Now, we see that a force F, that is this force F, we know that this force F here is suddenly applied onto the one sphere in the y direction. This is the y axis and this is the x axis that has already been created for us. That means again this is on the plane of the horizontal plane. So the gravity weights are actually coming down to this plane and are not contributing anything towards the motion which is taking place in the xy plane. So this force F is suddenly applied to one sphere in the y direction as shown and imparts a definite impulse of 10 Newton seconds during a negligibly short period of time. That means the time duration on which this force F is actually acting on the system is very, very small, but it is capable of providing or imparting a finite impulse of 10 Newton seconds during a negligibly short period of time. Now, as the spheres pass through this dashed position, so this is your initial position of the system, and this is actually the final position of the system, correct? So, as this system passes through this dashed position, we need to calculate velocity of each of the spheres. We need to calculate what will be the velocity of each of the spheres. So, again, you see, it is pretty clear from the statement of the problem that here the principle that we are going to use is the equivalence principle of, so we can say it is the equivalence principle of linear impulse, principle of linear impulse and linear momentum. So this is the equivalence principle of linear impulse and linear momentum. So in this case, we note that this force is acting along the y direction, and therefore if we just invoke our this equivalence principle, which states that it is coming from this equation that F bar E is equal to G bar cis dot. I am mentioning the relevant equation from where this principle is derived. So from here we can write this is integration from time t1 to t2. This is F bar E dt, that gives me the linear impulse, will be equal to G bar cis at time t2 minus it is G bar cis at time t equal to t1. So this is how we can, write this. This is what is termed as the principle of equivalence of linear impulse and linear momentum theory. So again, considering the fact that our force is acting along the y direction, so instead of taking the vector component, vector equation, what we can do is that we can write it, we can write it in the vector equation, of course. So we can say from here that this is going to be, say, integration considering the initial time as t equal to 0, which is this initial configuration, to delta t, where this is very small, we have f dt, and it is acting along the y direction, so it is j cap, must be equal to, we know that it will be m cis, or rather we, instead of considering this is m cis, we can write it like that. This will be equal to m1, we can say v1 along the y direction. So we can say this will be along the y direction, m1 v1 plus m2 v2 y all evaluated, this entire quantity needs to be evaluated for time t equal to delta t, right? Minus, we need to calculate the same quantity. This represents the total linear momentum of the system. So we can need to calculate m1 v1y plus, we can say, m2 v2y, and it needs to be calculated at time t equal to 0. So this is the thing, and of course this is in j cap direction, this is also j cap direction, and there is no force acting along the x direction, which means that the linear momentum in the x direction is going to be conserved. So we can say the linear momentum in the x direction is going to be conserved, and we can say that g sys x, the system's linear momentum along the x direction, is going to be equal to constant. That means it is initial linear, it is equated with the initial linear momentum. See, initially your system is initially at the condition of rest. So naturally what we can say from here, that this is going to be 0, or in other words we can say from here, that m1 v1x plus m2 v2x is going to be equal to 0 always. So this is our second equation that we are getting. This is our first equation we can write. And the first equation, if you recall, that initially everything was 0 because the entire system was initially at the condition of rest. So we can therefore say from here that m1 into, and m1 and m2 are equal. So that is the thing that we can write from here, that m1 is equal to m2. So since m1 equal to m2, we can simply write it to be equal to m. So we can say this is m into, we can write it in this manner, m into v1 of y plus v2 of y. This and the other thing is being 0 can be written as, this is the definitive impulse that we are getting. So the definitive impulse that we are getting is actually 10, how much impulse it is, it was saying 10 Newton seconds. So we can say this is 10. So 10 Newton seconds, we can write it like that. So we see from here that again we note from this geometry that since this is a rigid system assembly, the rigid system assembly, if we redraw it for you, we can show it like this. This is one mass, this is another mass interconnected by means of this light rigid rod. So since they are interconnected by this light rigid rod, it is to be noted that the velocity along this direction, so if we call this is the velocity, so if we show the velocity in the other color, so you see that if this is the velocity, we write it in this way. Suppose this is the velocity of the center of mass of this sphere. If we call this is v1, then the velocity of the second mass v2, right? If it is along the y direction, because y-axis is at the final, the axis along the rod. So this direction is taken as the y-axis. So you see these two velocities, they must be equal. Otherwise, this distance between these 2 points is not going to be constant. So we note from here, from the rigidity principle, we note that this v1y and v2y both will be basically equal, and we can write this to be equal to vy, right? So we can say from this equation that it is actually twice m vy is going to be equal to 10, or we can say that m into Vy is actually going to be equal to 5, or we can say that this Vy that is going to be equal to 5 divided by the each mass of this block is how much it is being given to be. So this is, you can say, suppose this is actually m2 and suppose this is equal to m1. So both these masses are equal and equal to 1.5 kg. So we can divide it by this 5 by 1.5 and can say from here that the common velocity, that means it is v1y as well as v2y, we see from here that they are having their velocities, and that is equal to how much? That is going to be equal to 5 divided by 1.5. So we can say this is 3.33 meter per second. So we can write it like that. That will be the velocity of the y component of the velocities in this direction. But is it the total velocity of these two particles? We note that it is not so. It is because we have some, this quantity here as well. So from this equation 2, we can say, so we can write from here that from equation 2, so we note from here that from equation 2, we can say equation 2, if you recall, this is actually our equation. So this is actually our equation 2. So from equation 2, we can say, from equation 2, we can write that since our masses are all equal, we can say that v1x plus v2x is actually equal to 0. That means the two velocities will be in the opposite senses, correct? Now, so here, up till this, we can actually have, up to this, we can extract the information only. But we do have another consideration in our hand. What is that? We note that this force is applied to this mass. And since these two masses are basically equal, we note that this is its center of mass, correct? This is going to be the center of mass, and the force is applied at a distance from this center of mass. So what does that mean? It means that apart from providing this linear impulse by this application of the force to this system, it is also able to provide the angular impulse to this system with respect to the center of mass, because the force line of action is at a certain distance away from the center of mass. How much is this distance? It is obvious that this distance is going to be equal to 300 millimeter. So that is the distance between these two. So thus we can apply here again the principle of angular impulse, angular momentum. Because here we have the angular impulse as well, because your force is applied at a certain distance from the center of mass. So here we can apply also. So now we note that F is also able to provide angular impulse to the system. So angular impulse to this system, and thus we can apply the principle of angular impulse, principle of equivalence principle of equivalence of angular impulse, angular momentum. So we can apply this principle also to solve our problem. So thus what we can write now, I do not show because we have already provided all these things. So I just show it from here that we can say that principle of angular impulse gives us the fact that it will be integration from time t1 to t2. We can say it is integration from time t1 to t2. We can write that it will be rho bar I cross f bar I, that is actually the moment dt. This is giving me the angular impulse. This is the moment, and its integration with respect to this is actually calculating us, for us it is h bar c at time t2 minus h bar c at time t1. That means here the moment is taken with respect to the center of mass. So this will be the moment of the force. This vector is producing this impulse, and that should be equal to the change in what is called the angular momentum of the system with respect to the center of mass. Now we just see from here that going back to this, we note that if this is the x-axis, that is the y-axis, we note that this will be the perpendicular line. Suppose this is our C, center of mass, and this is about the z-axis. So we see that this force is producing an impulse about the z-axis in this manner. Correct? So this is the the axis about which it is there, and when it is displaced and it is in this position, this will be the location of the center of mass, and the z-axis will remain the same. So this will be the the direction. This will be your z-axis direction. Your z-axis direction remains unchanged, and your angular velocity is also taking place about the z direction. And since we noted from the conservation principle of angular linear momentum along the x direction, we noted that the velocity of these two particles, correct, the velocity of these two particles in the x direction is going to be constant, right? And you know that when it is coming to this shape, so if this is your y-axis and this is your x-axis, so we can say that this is m1. So we can say that if the velocity of the one is, say, if the velocity of the particle 1 is in this direction, that means in the negative x direction, then the velocity of the second mass will be obviously in this direction, in order to have the fact that their velocities are negative. Here v1x plus v2x is 0. So what does that mean? It means that v1 of x is equal to negative of v2 of x. That means the two velocity, x component of velocities, will be in the opposite directions to each other. So we can say this is our, we can write this is our v1x, and this velocity we can write it as v2x. So they are in the opposite direction. So we can show them in this manner, like that. So we see that this effectively produces the impulse, the angular impulse, and this will be the mass times this will be your linear momentum. So this is your, we can write m2, and this multiplied by m1 will give you the linear momentum along the x direction, and their moment about this center of mass, we say this is c prime, about this moment about this point, if we take their moment, that means this distance is taken 0.3 meter. This distance is also taken to be 0.3 meter. That means we can write this is 0.3 meter as well as this is 0.3 meter. So we can take their, multiply them to get the angular momentum about the z-axis, which is about its positive direction. And here also we note that this force is producing a positive or the counterclockwise direction angular impulse with respect to this. So I therefore write from this above equation, I can say this above equation, when we are taking it about the z-axis, now we can write it like that, taking the component of the above equation, taking the component of the above equation about z-axis. In fact, this, if you express it vectorially, it will be only about the z-axis, because if we take up this express them vectorially, we will find that this entire moment and this entire impulse will be about the z-axis only, because you see this force is along the we note that this force is along the y direction, the moment arm is along the x direction. So obviously, therefore, the moment of this force is going to be about the z-axis, and that is going to be the positive moment, because it tries to rotate the whole thing in the anti-clockwise sense, and that's why the rod gets rotated in the anti-clockwise sense from its earlier position to this final position. So this is the sense of rotation of the rod. Because of this, the force is producing an anti-clockwise moment about the z-axis to this entire system. So that is the scenario. That's why the rod has taken, or the assembly or the system has taken this final configuration. The orientation is like this only. So therefore, we see from here that if we take this, all of them about the z-axis, then we can write this equation in a simple manner, that it will be 10 into 0.3, that will be equal to here, if you see this going back to our previous figure, we note that it is 0.3 into m1 v1x, and this will be m2 v2x, and we can further write this as, we say this is m into Vx, and this is also, we write it as m into Vx. Why it is so? Because the magnitudes of the x component of the velocities, they are equal. The magnitudes of the x component velocities are equal. Only thing, they have a negative sign in front of it, indicating that the two components will be in the opposite direction, as verified in this figure like that. So thus we can say it is 0.3. We can therefore write that it is going to be equal to 0.3 into 1.5 into V square. You see, this is 0.3 square. So 0.3, it will again multiplied by 0.3. So we see that this is 0.3 into 1.5 V, plus it is going to be another 0.3 into 1.5 V, not 0.3 square, sorry. So this is going to be like that. So it means that it is essentially 2 into 0.3 into 1.5. So we can write this is essentially 3 into 0.3 into V. So we can say from here that our V is going to be equal to, so we can say from here that we can cancel out this 0.3 factor from here and can say V, which is equal to V1x, that is also equal to V2x, correct? So this will be basically equal to, both will be the same, and that will be equal to 10 by 3. That means again it will be 3.33 meter per second. So this will be therefore the two velocity components of the spheres. So we say that both the spheres, we see if we write it in this manner, say consider this is the sphere 1, we note that, say this is the sphere 1, the sphere 1 we designated as the this sphere. So we see that their velocity components are something like this. We say that it is 3.33 meter per second, that is one velocity here, that is the y component velocity, that is 3.33 meter per second, the y component velocity, and we do have the x component velocity as also, that is 3.33 meter per second. Similarly, if we take into account the second sphere, we note that the velocity is in this direction. The y component velocity will be in the same direction of 3.33 meter per second. However, the x component velocity will be in this direction, and that is also 3.33 meter per second. So if we see that the total velocity of the sphere 1, if we see that will be the resultant of these two, vectors, that is going to be equal to the sphere 1's velocity. So we can say this will be going to be the sphere 1 velocity. So we can say this is v1, and of course if you find out the resultant of these two, we will be getting the sphere 2's resultant velocity, and we can say this is also equal to v2. So v1 and v2 both will be thus equal, and it can be written to be equal to root 2 times actually 3.33 meter per second. 3.33 meter per second. So ultimately what we can say that it is going to be multiplied by square root of 2. So sorry. So we can say that it is square root 2 into 3.33 turns out to be as 4.71. So we can say this is going to be 4.71 meter per second. So that will be our answer. So this will be going to be our answer for this problem. So let us go and check first the answer that is provided to our problem. So this problem is basically, it's a very good problem, little bit exhaustive than the previous two, little tough because you have motions in both planes, both directions actually. So if we see this 4 by 24, so open this and we see 4.71 meter per second both spheres, and our answer turns out to be as how much? That is going to be equal to 4.71 meter per second, exactly 4.71 meter per second. So that is actually, the velocities of the two spheres that we are having. So this problem, the last problem, is a very good one, where you see that we apply both these principles of the impulse momentum, and not only in this case we have the linear impulse of the system, we also have the angular impulse into our system, and that two together produce the net change in the velocity components, and you have to show every steps clearly in order to arrive at your answer. So dear students, with this we show you 3 problems, and we will like to give another shot taking 2 more examples, at least 1 example further, to show you another principle of this group dynamics. So hope when we will again meet, we will take up that problem to discuss further concept of the dynamics of system of mass particles. Till then, It's bye from my end, and thank you for watching the video.